And I'll stop my video. So today what we're going to be doing is we're going to be proving a bunch of theorems, mostly about Hermitian operators. And then we'll do some examples that should illustrate those theorems in action. Okay, so the first theorem we're going to prove is as follows. And I'm going to be using on purpose slightly different notation in class than in the lectures. I'll be using different letters, for example, for operators than what's in notes, just for variety. So let's say we have two operators, omega and lambda, and they commute. And let's say that little omega is an eigenvector of big omega. With eigenvalue, which is little omega. In other words, what we've done is we've named the vector after its eigenvalue. Okay, and then it's true that lambda acting on omega is also an eigenvector of capital Omega with the same eigenvalue. Okay, so the nice thing about this proof is it's a one-liner. So let's do it. So let's act with omega on the ket, which is lambda omega. Okay, so one way we can write that is it's, by definition, it's omega lambda omega. But since they commute, we can write that in the opposite order. We can write it as lambda omega acting on omega the ket. And because we know that little omega ket is supposed to be an eigenvalue of big omega, we can write that as lambda omega acting on omega, which is otherwise known as, because little omega is just a number, this is little omega acting on lambda acting on omega. So that line is just nothing other than saying that lambda omega here, when we act with omega, gives us back little omega, the eigenvalue, acting on the same vector. So that's literally the statement that we were supposed to prove. So as a corollary of this, if omega, the number, the eigenvalue, is non-degenerate, meaning it's the only one of that value in this theorem, then it must be true that lambda acting on omega is equal to lambda, a number acting on omega. The reason that has to be true is because omega is supposed to be unique. It's non-degenerate. It's the only one. And so little omega is also an eigenvector of the operator capital lambda. So we get 2 for 1. We get not only is it an eigenvalue of omega, it's also an eigenvalue of lambda if they commute. Okay, so in that theorem, we didn't have to assume anything about Hermitian or not Hermitian, but now we're going to be assuming that our operators are Hermitian. Okay, and so the first one, in the class notes, they're all numbered, but I'll just call them theorem. All eigenvalues, let's call them little omega, of a Hermitian operator. I guess in proper English, we're supposed to say an Hermitian operator, but that always sounds weird to me. Capital omega are real. Okay, so Hermitian operators have real eigenvalues. So here's the proof of that. suppose that in fact we do have an eigenvalue eigenvector pair of capital omega. So that's just saying that capital omega acting on little omega is little omega the number acting on little omega. And now what we're going to do is we're going to write down the statement that the matrix element in the ket omega of omega the operator is just equal to the number omega times the inner product. Notice we're not assuming that these are that omega is orthonormal, so we're not assuming anything in particular about little omega. But now what I'm going to do is I'm going to take the adjoint of both sides. So here on the left-hand side, I have omega, capital omega dagger, little omega. And on the right-hand side, it's omega star, omega, omega. So just to remind you of what the rules are for when you take an adjoint. So one thing you're supposed to do is replace every operator by its dagger. Okay, and you're supposed to change every bra into a ket. So that one turns into that one, but they're the same thing. That one turns into that one. This one turns into that one. This one turns into that one. And any number gets complex conjugated. So those are the rules of taking adjoints of both sides. But then, because it's Hermitian, omega dagger is just equal to omega. Okay, and so what we did here was we took adjoint of both sides. Okay, and so now what we've ended up with in the end is that omega minus omega conjugate acting on omega omega is 0, because the two things on the left-hand side were the same. Okay, and so that tells us that omega has to equal omega star. So there's one other way out, and that is if the inner product of omega with itself was 0, that would also satisfy it, but then omega would be in the null ket. And when we're finding eigenvalues and eigenvectors, we specifically exclude the null ket. That's just because the null ket is an eigenvalue, as an eigenvector of everything. So it's not worth worrying about. Okay, so that's the end of that proof. And now we can go on to another theorem. So all these theorems are going to help us understand later on how observables work in quantum mechanics, because in quantum mechanics, observables are Hermitian operators. Okay, so this theorem says if omega and lambda are Hermitian and commute with each other, and let's say we know that capital omega, the operator, has two eigenvectors. Let's call them omega 1 and omega 2 with different eigenvalues. So the eigenvalues omega 1 and omega 2 are not the same. Okay, then the matrix element of omega 1 lambda omega 2 is 0. So it's sort of magic. Just because we know something about the eigenvalues of omega, we know also something about the matrix element of lambda. The key thing is that lambda has to commute with omega. All right, so let's do the proof of this. So what we're going to start with is we're going to start with the matrix element of omega 1 with the commutator of omega and lambda. So I'm writing here the commutator, which is just the difference in the operators written in the different order. Okay, and what we know is that's 0, because this operator here is just 0. I've just written 0 in a fancy way. And so certainly its matrix element is 0. Which tells us that we can write omega 1, omega lambda, omega 2 is equal to matrix element omega 1, lambda omega, omega 2. And now the strategy is to act on, we're going to play with the left-hand side of this for a while. So this is the left-hand side of this equation. Okay, so what we're going to do is we're going to write this as the following. It's going to be the complex conjugate of omega 2, lambda dagger, omega 1. So really what I've done there is I've taken the complex conjugate twice, which is the same thing as what we originally started with. Okay, so when we take the first complex conjugate, we just change omega 1 into, we just change omega 1 the bra into omega 1 the ket, omega 2 the ket into omega 2 the bra. We dagger the operators and we write them in the reverse order. That's the same thing as taking the complex conjugate. And then we take the complex conjugate again to get back the original thing. So I haven't done anything in writing that left-hand side. Okay, but now I can write this because these are supposed to be Hermitian operators. I can write this as just omega 2, lambda omega, omega 1, complex conjugate. I've used the fact that they're Hermitian. Okay, and now omega acting on omega 1 is equal to omega 1 acting on omega 1, or multiplied by omega 1. So this is equal to omega 1 star, because I've complex conjugated it, times omega 2 lambda omega 1 complex conjugate. Okay, and on the other hand, we had the right-hand side here. This was equal to omega, let's see, sorry, omega 1 star, omega 2 lambda, omega 1 star. Sorry, this is equal to, now I can write this as omega 1 lambda dagger, omega 2, which is also known as omega 1 lambda omega 2 times omega 1. Okay, and so in the end, what we get is omega 1 minus omega 2 multiplied by omega 1 lambda omega 2. In both cases, we have that matrix element. That's supposed to equal 0. Okay, and so because omega 1 and omega 2 is supposed to be non-zero by assumption, that means that the matrix element omega 1 lambda omega 2 has to be 0 in order to satisfy this equation. Okay, so there's a corollary of this also that's particularly useful. And that is, let's say omega is Hermitian.
Professor, hold that thought just a second. I'm sorry. Can you say again what we did with the right-hand side? Did we just say that it equals 0? Or?
Oh, let's see, what did I do with the right-hand side? You mean, let's see, you mean up here?
Yeah, so what did we do with that?
Right, let me figure out what I'm doing there. Oh, right, sorry, I didn't finish that thought. Very good. Okay, so that was omega acting on omega 2 is, my pen keeps changing, is omega 2 times the matrix element omega 1 lambda omega 2. So I've used the fact that omega acting on omega 2 gives the eigenvalue omega 2 multiplied by omega 2. Sorry. And then,
okay.
and then that's where, I think I have a typo here somewhere. Let's see. Ah, right. This should have been, thank you for pointing this out. This should have been omega 2. And then that's where this omega 2 came from, because I moved it back to the other side of the equation. All right. Okay, are we good? I hope so.
Yep, I would say so.
Okay, so the corollary says if omega is Hermitian, oops, gotta go back to my pen. If omega is Hermitian with eigenvectors omega 1 and omega 2 with different eigenvalues again. So omega 1 is supposed to not be equal to omega 2. Then the inner product of omega 1 with omega 2 is supposed to be 0. Okay, so how do we prove that? It's a corollary, so of course we're going to use the previous theorem. And the proof is just we take lambda to be the identity operator in the previous theorem. Okay, and that works because the identity operator is Hermitian. And the identity operator always commutes with every other operator, so it certainly commutes with omega. And so the requirements of the previous theorem are true. And so now we can just apply it, and then this lambda here just becomes 1, and we're just going to have the inner product rather than the matrix element as we did in the theorem. So this is in previous theorem. Okay. Let's go on with another theorem. This is all a bunch of theorems, but I promise we'll do an example in a bit. So the next theorem is, let's say omega is Hermitian, but now I'm going to make an additional assumption that the dimension of the Hilbert space is finite. Then you can form an orthobasis from its eigenvectors. Okay, and this orthobasis is unique if the eigenvalues are non-degenerate, meaning they're all different. Okay, in that orthobasis, what that means is we're going to be computing matrix elements between different orthobasis elements. In that orthobasis, the operator omega is diagonal. Okay, so to do this, what we're going to do is we're going to construct this matrix whose columns are the components of the orthonormal eigenvectors. And look at what it does. So matrix whose columns are components of the orthonormal eigenvectors. And so what I mean by that is, if I've got this matrix that I'm going to call U, and I look at its JL entry, and this we're defining to be the jth component of the lth eigenvector. Okay, so maybe it's better if I put parentheses here. So the first thing you do is you find the lth eigenvector, then you find its jth component, that's some number, and that's what's UJL. And so we're going to write this matrix out as just U11, U12, up to U1n. This is where it's important that it's a finite dimensional thing. Otherwise, this would be an infinite dimensional matrix, which would be hard to deal with. Okay, and I guess this is UNN. Okay, and because this is supposed to be built out of components of the eigenvalues and eigenvectors, we can write the eigenvalue equation in matrix form. Okay, and so the way that looks is if you sum over k, omega jk, acting on UKL. So if we imagine fixing the index L just for the moment, then UKL are the components of the eigenvector. And then this is just matrix multiplication acting on the eigenvector. So that's going to equal the eigenvalue. We fixed L. So omega L is the eigenvalue multiplied by the eigenvector components again, omega JL. And so now what we're going to do is just rewrite this as a sum over, let's call it L prime of UJL prime. I'm going to write a Kronecker delta, delta L prime L, and then omega L. Okay, so this, let me, I guess, highlight it here. That part is a diagonal matrix, right? Because it's only non-zero if L and L prime are the same. Okay, and so I'm going to call this matrix, this diagonal matrix, I'm going to call omega diag. Okay, and so what have we got here? This is right here. Okay, that's matrix multiplication. And so that says omega, the matrix, acting on U, the matrix, is equal to, over here, that's the matrix U again. Oops. That's the matrix U again, acting on this matrix omega diag. And just to be explicit about what omega diag is, excuse me, omega diag is equal to the matrix whose diagonal entries are the eigenvalues, omega 1, omega 2, up to omega n, with zeros everywhere off the diagonal. And so we're almost done. The last thing we have to do is just multiply both sides on the left by U dagger. And so this is U dagger, omega U is equal to omega diag. Okay, so in words, the way we describe what we've just done is we say that the matrix U diagonalizes the operator or the matrix omega. Okay, so again, just to review, what did we do? We said, let's say we know what the eigenvalues and eigenvectors are of omega. We constructed this matrix omega out of them. And and that gave us that gave us this boxed equation, which tells us how to make a diagonal version of omega, omega diag, out of omega itself. Now, when we constructed U, there was no guarantee necessarily that it's unique, but it is going to be unique unless two of the eigenvalues are the same. So it's not unique if some omega j are equal. And the reason it's not unique is just because if they're equal, you can do further unitary rotations. So because can do further unitary rotations, within the degenerate subspace. In other words, acting on only the vectors that have degenerate eigenvalues and not the other ones where it's just the identity. So we'll do an example of that in a little bit. But when you do those further unitary rotations, it keeps omega diagonal, just because the basic reason for that is because those further unitary rotations are only acting on a subspace where omega diag is proportional to the identity matrix, and any unitary rotation will keep that fixed. Okay, so now let's just let as some notation j, where j is 1 up to n, be an orthobasis with components that we're going to represent in the following way. So for j equals 1, it's just going to be the vector with 1, 0, 0, 0 all the way down. That's j equals 1. For j equals 2, it's going to be 0, 1, and then all the others 0. And then etc. So for the last one, it will be zeros all the way down, and then 1 in the last entry. That's for j equals n. Okay, then omega j, the ket, is equal to our unitary operator acting on the basis ket, j. Okay, so this is the unitary operator, which we are specifying by telling what its matrix elements are. So with matrix elements ukj equals k u j. All right, so let's do the promised example, because I think that will tend to make things clearer, and this will actually be somewhat similar, more than somewhat similar to your homework problem. Okay, so in our example, let's let omega have a matrix representation in the orthobasis. Instead of calling it 1, 2, 3 for variety, I'm going to call the orthobasis A, B, and C. And we're saying the operator omega is going to be represented. I put this double arrow to meaning the operator is associated with the matrix. It's going to be 1, 0, 0, 0, 2, I, 0, minus I, 2. It's my example, so I get to pick it. Okay, and so what does that mean? That means that if I act with omega on the ket A, I just get A back. That's the 1 here. with the zeros as well. If I act with omega on the ket B, I'm going to get 2 times B minus I times C. Okay, and so really that's this column of the matrix. And then omega acting on C is equal to I times B plus 2 times C. And so again there, we're just reading off from the column of the matrix representation. Okay, so what if I know the matrix representation, then I know how the operators act on the different basis kets. Another way of writing this, another way of writing this.
Professor?
Yes, go ahead.
I'm a little bit confused. Like I said, my math isn't too good. Wasn't it the what do you call it, the row times the column?
So no. So what you have to think of is, for example, in the case of B, you're taking this matrix and you're multiplying by. So let's say I multiply by B. I'm multiplying by this vector. Oops. Okay. And so the things that will survive are the columns. This will give me 2. This will give me 0 for the first one, and then 2 for the second entry, and then minus I for the third entry, multiplied by the third vector, which is C. So that's why it's the columns that come in. Okay. Yeah. So it takes a little getting used to. It looks like you're sort of transposing the matrix when you write it in this form, but that's the way it works. If you get confused, what I would recommend doing is just literally writing out the matrix multiplication as a check. Okay, so in any case, another way of specifying this is just to give a complete list of all the matrix elements. And that would be as follows. A omega A, that's a matrix element, is equal to 1. That's from here. Okay. A omega B is equal to 0. A omega C is equal to 0. B omega A is equal to 0. B omega B is equal to 2. And B omega C is equal to I. And that we're pulling out, that we're recognizing from this entry. Okay, and then we can just finish it off. C omega A is 0. C omega B is minus I. And C omega C is 2. Right, and just to remind you where this can come from in the notes, you can see equation 2.5.6 in the notes, where the matrix elements were actually defined. Okay, so in this example, one of the things we're going to want to do is find the eigenvalues. That comes from the characteristic equation. Okay, which in this case means the determinant of 1 minus omega, 0, 0, 0, 2 minus omega, I, 0, minus I, 2 minus omega. Okay, and this is a 3x3 matrix determinant, so this is going to be a cubic equation. But fortunately, I've engineered the example, so it's not too horrible, because it factorizes into 1 minus omega times 3 minus 4 omega plus omega squared. That should equal 0. And now it's a quadratic equation times a linear equation. And so the solutions are omega equals 1, and omega equals 1 again, and omega equals 3. Those are the three solutions of the cubic equation. And we recognize that, again, I've engineered this example so that two of them are the same. So we have a degeneracy. Okay. So now that we know the three eigenvalues, even though two of them are the same, we can go ahead and construct the eigenvectors. Let's do the non-degenerate one first. Those are usually easier. For omega equals 3, the eigenvector that you get just by writing out the matrix form is 1 over root 2, 0 I, oops. Okay, that's the matrix representation form, or I can write it in ket form as omega equals 3 is equal to I times B plus C all over the square root of 2. So that's our first eigenket for the omega equals 3 eigenvalue. And notice I've named the vector, I've named the ket after the eigenvalue by calling it omega equals 3. For omega equals 1, there are two eigenvectors because there are two eigenvalues. And they are 1 over root 2, 0 minus I1. And the easy one actually is just 1, 0, 0. So once you've found the 1, 0, 0 one, you require the other one to be different than that. Okay, and so I can write this in the following way, that I have one ket, which is omega equals 1, 1, which is going to be minus I times B plus C over square root of 2. And the other one's going to be omega equals 1, 2, which is just A. That comes from the second one. Okay, so now, just to explain the notation, I've got one label which tells you the eigenvalue, which is omega equals 1. And then there's a second label, which is 1 and 2 here. Those are labels for the degenerate subspace. They tell you which of the two vectors in the degenerate subspace you're talking about, 1 or 2. Okay, so as the theorem promised us, these are orthonormal. Okay, and actually the theorem just told that they had to be orthogonal if the eigenvalues are different, but the factors of 1 over square root of 2 were chosen to make it so. Okay. Now, it might be that that you're not sure when you've constructed the vectors whether they're orthonormal, but what you can do is just rescale them, and or you can always just apply the Gram-Schmidt procedure to make sure that they're orthonormal. Okay, let's just do some checks to make sure. So let's say I take the matrix element, or sorry, the inner product of the omega equals 3 vector with the omega equals 1, 1 vector. So that's as follows. For omega equals 3, it's minus I B plus C bra over square root of 2. Notice that what I did here is I took the complex conjugate of this I because I was changing, or I was finding the bra associated to a ket, so I always take the complex conjugate. And then for omega equals 1, 1, I'm just plugging in this. Okay, so that looks like minus I B plus C all over square root of 2. Okay, and so that's minus 1/2 minus I squared over square root of 2 squared times the inner product of B with B plus 1/2 1 over square root of 2 squared times the inner product of C with C. I don't have to worry about B with C and C with B because this was an orthonormal basis. So note BC and CB were both 0 because of orthonormality. Okay, and so this is 1, and that's 1. And so that's by advanced methods, minus 1/2 plus 1/2 is 0. Okay, so that's what was supposed to happen. I have eigenvectors of a Hermitian matrix with different eigenvalues, and they are orthogonal, as they're supposed to be. Okay, now we can do, as another check, we can do the inner product of omega equals 3 with itself. Okay, and so that's equal to minus IB plus C over square root of 2, just like we did in the previous check, times IB plus C over square root of 2. And then that works out to 1/2 B with B plus 1/2, oops, C with C. Okay, and again, this is 1, and that's 1, so that's 1/2 plus 1/2, which is 1. So again, that checks. And that's how we knew that these factors of square root of 2, or how I knew that these factors of square root of 2 had to be there. If you're working a problem, it may not be obvious. And so what you want to do is compute the inner product of something that's supposed to be orthonormal with itself. And then that will tell you what the overall factor is that has to make it end up being 1 in the end. Okay, so then you can do all the other, I won't do all 9 cases. So I'll just say et cetera here. But they are a set of orthonormal vectors. Now, on the other hand, as I also mentioned, they're not unique. And so let's just illustrate why they're not unique. Okay, so for any complex x and y, just any complex numbers, we can make a new set of orthonormal eigenvectors. The first one I'm going to call omega equals 1, but instead of calling it 1 or 2, I'm going to call it 1 prime. And I'm going to construct it as follows. It's x times omega equals 1, 1 label, plus y times omega equals 1, 2 label. Okay, and then to make this thing be orthonormal, meaning to make it have norm 1, I'm going to multiply by a constant, which is going to be 1 over the sum of the square roots of the magnitudes of x and y. Okay. And so similarly, for omega equals 1, 2 prime, so this is a different label, 2 prime, I'm going to make it be minus y star, the complex conjugate, omega equals 1, 1, plus x star, omega equals 1, 2. All divided again by this square root. Okay, so what I've done is I've chosen these coefficients, x and y, and this crazy square root, because I know that this is going to make them orthonormal. So you can check that they both have omega eigenvalues, omega equals 1. That's basically because everything in this subsector has eigenvalue 1 for omega. They're also orthonormal. You can just do that check that by taking every pair of matrix of inner products. And so the new labels, 1 prime and 2 prime, are just to distinguish them from the old labels. Distinguish. the degenerate kits. Okay, so another way of saying what we did there is we define a unitary operator. Let me call it U for unitary, in the following way, that omega equals 3 is the unitary operator times omega equals 3. So on that subspace of the 3 eigenvalue, it doesn't do anything, it's the identity. And then omega equals 1, 1 prime is U acting on omega equals 1, 1. And omega equals 1, 2 prime is U acting on omega equals 1, 2. So these equations put together define my operator U. Okay. So now you can work out what are all the matrix elements of U. And so, for example, omega equals 3, U omega equals 3 is just 1. Omega equals 3, U omega equals 1, 1 is 0. Omega equals 3, U omega equals 1, 2 is 0. Omega equals 1, label 1 with U omega equals 3 is 0. Omega equals 1, 1, U omega equals 1, 1. This is the first sort of non-trivial one. This is x over the square root of x squared plus y squared. Okay? And you can keep going for all the rest of them. Or a prettier way to write things is in matrix form. Okay, and so we're working in the original basis. Omega equals 3. Omega equals 1, 1. Omega equals 1, 2. We're working in that basis. Then the matrix form for the operator U is 1, 0, 0, 0, x over, I'm just going to write square root for that square root. It's the same every time. Minus y star over square root, 0, y over square root, and then x star over square root. Oops. Okay, and then as a check that this is really a unitary matrix, you can take its dagger, which means complex conjugate transpose in matrix language. So it looks like this. Okay, so the dagger means complex conjugate transpose in matrix form. Okay, and then it's easy to check that U dagger U and U dagger are both equal to 1. So it is indeed a unitary matrix. Okay, so the way we can talk about this is we say the two orthobases of omega eigenkets are related by a unitary transformation. Whenever you see the words unitary transformation, you should think change of basis. That's what a unitary transformation does for you. That act in the degenerate subspace. So acting in the omega equals 1 degenerate subspace. All right, so that's it for today. I think hopefully you'll find that example to be somewhat similar to some of the things you get to do for homework. And so next Monday is indeed a holiday. And so you'll have, we have no class that day, but we've gone over everything that you need to do the homework. So let me know if you have any questions by email, or we can set up a Zoom if you want. One thing that somebody pointed out to me is that I've replied to every email I get, but somebody wasn't getting them, and it's possibly because of spam filters. So if you expected to get an email from me and you haven't, check your spam, because it seems like NIU has, I think, been very aggressive lately about filtering out spam, and my emails come from a Gmail account, so they might be getting filtered out. Okay, so if there are no other questions, then we'll be done for today.
Thank you, Professor. I got a question on page 13 of the note.
Okay, sure. Let me stop the recording here.